Welcome to our second webinar on bus protection. Today, specifically, evolution of bus protection for a modern grid. I am JC Theron, Lead Product Manager with GE Digital Energy based in Markham, Ontario, Canada. My main accountabilities are product management duties on the UR and UR Plus protection families of relays, specifically including bus protection. In our first webinar on bus protection, we covered specifically what's the importance of bus protection. Why is it necessary to be fast? And we covered specifically arc flash mitigation. Then we also had a look at high impedance versus low impedance and how bus protection schemes evolved and how low impedance is becoming much more implementable and getting much more specified. We also had a look at centralized versus distributed bus protection scheme and how distributed bus protection schemes are evolving as 61850 process bus. We also covered enhancements in bus protection and how the capabilities of such bus protection devices evolved to add waveform capture and oscillography and sequence of event recording. In today's agenda, we'll have a look at the configuration of the low impedance bus differential zone and specifically the meaning of each of the settings that's important to define this zone. Then we'll have a look at the adaptive logic of the bus differential and how it works. Then we'll cover application considerations for the B30, the B90, and the B95 Plus, and we'll have a look at the differences and the comparisons between the different devices. Then we'll end the webinar with some advanced application topics such as isolator monitoring and in-fault protection. Let's start off with the configuration of low impedance bus differential. In configuring the bus differential zone, there are a couple of aspects that has to be taken into account. Now, first we might need to step back a little bit and have a look at what the bus differential zone specifically looks like, our differential versus restraining characteristic, and we're going to cover all these settings. But before we can get to that part, configuring the physical CT inputs is very important, of course, and these CT inputs will be based in signal sources for the B30 and the B95 Plus, and that has to be configured because the bus differential zone, the signal sources has to be assigned to it. Then configurable bus zone with dynamic bus replica we'll cover after that. Now, before we dig into those details, let's have a look at some restraint methods, sum off versus max off restraint. Now, max off approach, the advantages are it's less restraint on external fault, however, it's much more sensitive for internal faults. Breakpoint settings are easier to calculate and it copes well with CT saturation. And the max off approach, that's specifically what we follow and use in our B30, B90 and B95 Plus devices. Let's have a look at bus differential adaptive logic. Now, the bus differential characteristic, we can split it up in two regions, a region 1 and a region 2. And region 1 has low current magnitudes. Now, CT saturation is unlikely to occur in this region. It's typically due to DC offset. However, it's more difficult to detect. Region 2 has much higher current magnitudes. CTs typically saturate likely in this area, and it's much easier to detect CT saturation in this region. Now, based on these two regions, we have an adaptive logic to determine how the differential scheme will operate. Now, region 1, we need more security, so that's why we need to use a directionality check. Now, region 2, security is only required if CT saturation is detected, and it dynamically decides if a 1 out of 2 or 2 out of 2 operating mode is necessary. Now, the directionality check that we're referring to is based on the angles between all the different currents and not voltages. So it's not similar to a phase directional function. It is the direction of all the currents compared to each other. Now, the principle is if we have an external fault, even with one CT severe saturated, we'll see one current well in the blocking region, where with all internal faults, we'll see all angles of all currents well in the operating region. Let's have a look at what happens during CT saturation based on our differential characteristic. Typically at load conditions, at time t0, we will have very little differential and a little bit of restrained current based on load conditions. Then during an external fault, we'll first see a significant increase in restraining current and, of course, due to CT error on the differential, until the CT starts to saturate. And when the CT fully saturated, our restrained current magnitude will actually reduce and our differential current will significantly increase, bringing us into the operate region. And this is the part the differential algorithm has to be safeguarded against. Now, and that's why we use the directionality check. So the saturation flag is not set during internal faults, regardless whether CT saturation is detected or not. However, the saturation flag is set during all external faults, regardless of CT saturation or not. So by design, the saturation flag forces the use of an additional directionality comparison check for region 2. So what this means is the saturation flag, it does not block differential specifically, it just forces a 2 out of 2 operation. Let's have a look at some actual CT saturation detection examples. So in the next 2 slides, we'll have a look at some actual waveforms captured by a B30 during simulator testing. The first slide is for an external fault where we have actual deep CT saturation, and we'll have a look at the performance of the algorithm. And the second slide is for an internal fault with some mild CT saturation. So for the external fault, this is what the CT currents look like. And in this case, we can see one of the phases saturated significantly within 1 millisecond. But despite this, the bus differential protection element, it will pick up during the CT saturation. However, the CT saturation flag is set safely before the pickup flag, and the directionality flag is not set. And based on this, the differential element would not operate as expected. And looking at the directionality check and the phase angles of all the currents, we could see clearly, despite the heavy CT saturation, that one of the angles is clearly in the opposite direction, meaning it's an external fault and the element blocked. Let's have a look at the internal fault example. In this case, we can see some CT saturation. However, the bus differential element picks up very quickly. CT saturation flag is not set because the directionality flag is set indicating it's an internal fault and the element operates in 10 milliseconds. In this case, we can see all fault current angles are more or less in the same direction, indicating clearly that it's an internal fault. Let's have a look at some application considerations specifically for the B30, the B90 and B95 Plus. First of all, we'll have a look at some basic topics, such as configuration of the physical CT inputs, the dynamic bus replica, the bus zone and how to configure it, and then calculation of the bus differential element settings, and we'll cover them one by one. And then we'll end off the webinar with some advanced topics. So first of all, configuring the CT inputs, it is of course important to enter primary and secondary ratings. Now for the B30 and the B95 Plus, this is done on a 3-phase CT bank, and each CT bank has to be assigned to a signal source. And these sources then has to be assigned to the bus differential zone, and also for the dynamic bus replica. For the B90, each CT channel is directly assigned to the zone and dynamic bus replica. So in this example, this is for a B90, we can see that CT F1, the primary is 3200 and the CT secondary is 1 amp. Now, what's important to note before we can discuss the differential settings, all settings are in per unit. So the question is, what is 1 per unit? And for all our relays, it's the same principle. And the answer is, it's the maximum primary setting. For example, in zone 1, we can see the maximum primary current is 3200 amps. And for zone 2, it's 5000 amps. So that's why 1 per unit for zone 1 is 3200 amps, and for zone 2 is 5000 amps, and this is not based on the CT ratio, but the maximum primary current. Let's have a look at the configuration of the bus zones specifically for dynamic bus replica. Now, each feeder or current has to have a status signal to associate it with the bus zone specifically. And the status signal can be either a flex logic operand. Typically it would be an isolator position. Now for the B30 and the B95 Plus, each signal source must have an associated status signal. However, for the B90, each channel has to have its own associated signal specifically. And what also needs to be configured is the direction of our currents, whether it's in or out of the zone depending on CT polarity. Let's have a look at an example. So the dynamic bus example, in this case, we can see, if we have a look at North Bus, feeder C1 will always be part of North Bus because the CT is always associated with it. However, feeder C2 will only be part of North Bus if isolator S1 is closed. And this is what it looks like in the configuration software. So we can see CT1 is on, CT2 will only be on if S1 is closed. And this is actually how it would be configured in a B90 configuration file. So similarly, C3 will be part of North Bus if S3 is closed. And same with C4 will be part of North Bus if S5 is closed, as it is configured in this case. And the same has to be done with all feeders that potentially will be part of the bus. In the next couple of slides, we'll have a look at the bus differential characteristic settings, specifically focusing on 6 crucial settings that is important to define the differential characteristic. The first setting is just referred to as the pickup, or also called the minimum pickup, which defines the differential current the bus differential element will operate at. Now this current must be above the leakage current that can occur that's not part of the differential zone. For example, if there's a voltage transformer or an auxiliary transformer that's not part of the bus zone, the pickup has to be set above that maximum current that can occur, else the scheme can misoperate. And this may be above the maximum load for security for CT trouble purposes. However, there are better options. The range is typically in 0.05 to 2 per unit. The next setting is the low slope, which is specifically spanning from close to 0 or intersecting with the minimum pickup all the way to low breakpoint. And this defines the region typically during load conditions where we can have a much more sensitivity for low differential currents. Now this must be above maximum CT errors in our normal linear load operating area, and of course is well below any possible CT saturation conditions. The next setting, the low breakpoint, this defines the upper limit of our low breakpoint. And this should be above the maximum load conditions, however, not more than the maximum linear CT currents, including residual flux. And for this, the assumption is that the CTs will operate linearly with no significant saturation up to 80% of residual flux up to low breakpoint setting. So it's important that we know up till this point there will be no CT saturation. And the range for this is 1 to 4 per unit. Now the high breakpoint defines the minimum restraint current that is necessary for the high slope. Now this should be set below the minimum current where the weakest CT saturates with no residual flux. In other words, the weaker our CTs, the lower our high breakpoint setting will be. Now keep in mind, this is also an assumption that CTs operate linearly, in other words, no significant CT saturation up till 80% of residual flux for up to low breakpoint setting as we've seen before. Now, the range for the high breakpoint is typically 4 to 30 per unit. Then the high slope defines the percentage bias to restraint for current larger than high breakpoint. In other words, is our area above our high breakpoint to the right of that. And this setting determines the stability of the differential elements for high external fault currents. And this should be set high enough to tolerate spurious differential currents during saturation of CTs on heavy external faults. Now, the good question is, what should this setting be? Is 75% good, or should it rather be 99%? Now, this setting can be relaxed in favor of sensitivity and speed, as CT saturation and the directionality principle will be used for security. In other words, it's not necessary to set it too high. Now, the range of this is 50 to 100%. Then the last setting is the unrestrained differential settings, which define the minimum differential current for unrestrained operation. And this should be well above the maximum differential current under worst case CT saturation, because this operates without any restraint. The range is typically 2 to 99. Now, if this setting needs to be disabled, just set it to 99.9. We always get the question that in an example, if we have a B30, which we know has the capability for up to 6 feeders, if we add a 7th circuit, can we do this? Now, the problem is the only way to do it is to parallel the two of the CT sources to the relay. And if we do that, the relay becomes a combination of restrained and unrestrained elements. So it could be done, however, it's generally not recommended. It's rather better to extend the scheme and use other products such as the B90 or B95 Plus. However, if CTs are paralleled, CT performance, of course, must be identical. Associated feeders must be radial, in other words, no feedback can be tolerated, and pickup settings of the differential has to be raised. It has to be made less sensitive to compensate for this spurious differential that we can see in this case without any restraint current. In the next section, we'll cover some advanced application topics, specifically such as isolator and isolator monitoring. We'll cover a little bit more on dynamic bus replica, blind spot, in-fault protection, and why and where it is important. Then we'll have a look at a fairly new function for each differential zone, which is the CT trouble. And then we'll end off with some additional security for the bus differential zone, for example, external check zone, under voltage supervision, and overcurrent supervision. Let's start off with isolators. Now, a reliable isolator closed signal is needed for the dynamic bus replica, and it's very important, especially on high voltage and extra high voltage. It's typically not that important on medium voltage. So, in other words, a simple single normally closed contact may not be sufficient. So for maximum security, rather use a normally open and a normally closed contact. And if both of them are in a non-valid combination, for example, both are open or both are closed, then we have to have the ability to alarm for it and inhibit switching of the bus image until the isolator position is reliable. And during these alarm conditions, have the ability to block the differential in those cases until the image is reliable. Now, why it is important that we know the position is for each current, because the current is used in the differential calculation, and the circuit breakers is also tripped based on this position. That's why the isolator position is so important. Now, typically how it would be wired to a B90 in this case is just simply the A contact and the B contact would be wired to two separate contact inputs, as is shown in this case to a B90. The full-featured isolator monitoring capability that we have in the B90 and B95 Plus works roughly as follows. If we look at this table, our isolator open aux contact, isolator closed aux contact, if we have the combination off-on, We know the isolator is in the closed position. We do not have to alarm or block switching. And same if we have it in the on-off configuration, then we know the isolator is open and no need to alarm or block switching. However, if both are off, then the isolator is deemed to be in the last valid or known position. And if both are on, then we deem the isolator to be closed. But in both those cases, the isolator will alarm. And it will only reset if the alarm gets reset, but the block switching will occur until the isolator position is valid. Now, for the B30, this needs to be implemented in flex logic. In other words, it's not a standard feature of the B30. However, there are 48 dedicated isolator position monitoring elements in the B90. Let's have a look at what an actual closing sequence would look like. If we look at isolator 1 open and isolator close signals, then we'll always have to allow a time delay for a transition for when the isolator operates. But if in this case the isolator did not close successfully after a time delay, we will alarm and we will block at the same time. But let's say we did acknowledge the alarm will clear, however blocking will remain until the isolator position is in a known state again, as in this case it went back to the open position. Let's have a look at dynamic bus replica and the changing of the bus zone. So in this example, we have a typical bus tiebreaker with two CTs. There is a very good overlapping of zones of zone 1 and zone 2. So there are no blind spots. Both zones strip the tiebreaker. So this is normal case. No special treatment of the tiebreaker is required. We don't have to do anything special. However, let's have a look at this case that in some transmission applications for economic reasons, only one CT might be available. So in this case, we still have both zones must trip the tiebreaker. However, there is a blind spot between the CT and the tiebreaker in specifically this area. So in other words, we'll have to do something special in this case. Now, zone 1, no special treatment is necessary. It just acts as a regular zone and treat the tiebreaker as a regular circuit breaker. However, zone 2 special treatment of the tiebreaker is required for the tiebreaker status. So in this case, the CT must be excluded from the calculations after the tiebreaker is open, and meaning zone 2 gets extended or opened entirely onto the tiebreaker. So in this case, we can see zone 1 tripped the tiebreaker as it normally would. After a time delay, the current from the CT shall be removed from zone 2. In other words, we extend it up until this area. So as a result, zone 2 covers up to including the tiebreaker, including this blind spot. So the fault becomes internal for zone 2 and zone 2 trips, finally clearing the fault. And that's important in this case because zone 2 definitely we will see fault current from this direction into the fault, and that's the only way we can ensure the fault current gets cleared. Now a blind spot can also exist between a current transformer and a circuit breaker in this configuration, similar to what we saw in the bus tie with the circuit breaker configuration. So in this case, the circuit breaker can be tripped by a line protection, and after the circuit breaker opened, the current must be removed from the differential calculation, expanding the differential zone to cater to cover this blind spot as well. So it's identical to the single CT tiebreaker situation. However, what happens if the CT is on the other side of the circuit breaker? Then we can have this area as a blind spot, and which can be seen as an overtrip spot. So in this case, when the circuit breaker opens, currents must be removed from the differential zone, contracting the differential zone all the way to the circuit breaker. So this is identical to the single CT tiebreaker configuration. However, a blind spot is created when contracting this differential zone. And this is exactly why in-fault protection is needed. Now, in-fault protection is an instantaneous overcurrent element that's enabled when the associated circuit breaker is open, and of course its purpose is to cover this blind spot. Now, it must have a pickup delay that should be long enough to ride through the ramp down of the current the relay will see when the circuit breaker open. And in-fault protection must be inhibited from circuit breaker manual close commands, and it's something that is not available in the B30, so it must be implemented using flex logic. However, in the B90 and B95 Plus, we do have 24 dedicated in-fault protection elements. Each bus differential zone in the B30, B90, and B95 Plus has a dedicated CT trouble monitor. Now, as we've seen in webinar 1, the B30 has 2 zones, B90 has 6, and so does the B95 Plus. Now, the CT trouble is a definite time delay overcurrent element based on the zone differential current. So it's a low current based on the configured dynamic bus replica, in other words, the status of the bus. Now, there are 3 strategies to deal with CT problems. The first one is trip the bus zone, as CT problems will likely evolve into a bus fault, which can occur in brownfield installations where we have older CTs and wiring that could cause errors and faults. Second option is do not trip the bus, however, raise an alarm and try to correct the problem manually. Or the third option is switch setting groups with the differential pickup settings above load current conditions. Now, strategies 2 and 3 can be accomplished by using under voltage supervision to supervise the differential during CT trouble, use an external check zone to supervise the differential, or use CT trouble to prevent the differential from tripping. Another option is raise the settings by switching to a different settings group with much higher settings. Now, good question is, could CT trouble be used to block the differential input? And the answer is it should not be done. For the reason is the differential trace is based on the differential restraint point, and the movement is important to be monitored for CT saturation detection. Hence, it should not be turned on and off. Instead, it's better to use supervision in flex logic. Here's an example of how to use strategy 2 of CT trouble. So in this case, we have our bus differential operand and also an under voltage condition supervising the differential together with CT OK, which is the CT trouble not operand. So in this case, the CT trouble operand is used to raise an alarm and the differential inhibited after the CT trouble element operates. However, under voltage is still used to supervise the differential function. In this section, we'll address some additional security for bus differential protection relays. No matter how reliable a protection relay is, the mean time between failure is never enough. Any relay misoperation or bus protection misoperation is detrimental and has detrimental consequences. So the following contingencies should be considered. CT problems and CT wiring, AC wiring problems has to be checked. Problems with auxiliary switches for breakers and isolators. DC wiring problems involving the dynamic bus replica and failure of relay hardware such as current inputs and digital inputs has to be monitored. Now, we already have much more security than in the past. For example, we have the CT saturation detection and the directionality check to secure the differential algorithm, and we also added isolator monitoring, but in some cases this is still not enough. That's why the first way of additional security is using an external check zone. So in this case, we have to develop an independent copy of the differential current for the entire bus, regardless of what the state is of the dynamic bus replica. And in this case, use a check zone to supervise the tripping zones. And it's recommended to use independent CTs or, if possible, additional CT cores to safeguard against CT and CT wiring problems, and use independent relay current input to safeguard against relay problems. And if we do see a difference, then we should alarm on that. And this would safeguard against CT problems, wiring problems associated with the CTs, and problems with the auxiliary switches for the breakers and the disconnects. It would also guard against the DC wiring problem for the dynamic bus replica associated with the isolators and isolator monitoring, and also safeguard against failure of the current inputs of the relay. Here's an example of how an external check zone can be done in the B30. Now with 6 3-phase current inputs, the B30 can handle up to 2 zones of protection, and the actual tripping zone can be configured to reflect the dynamic image of the bus if necessary. However, as we've seen, logic is necessary to determine that. Now, an external check zone can be configured as an unrestrained zone using separate CTs and CT cores. In other words, we can use the instantaneous overcurrent function to operate on externally summated currents. However, it would be important to note, to do this, the CTs would have to be identical or auxiliary CTs would be required. So to do this, we can use 3 ground CT inputs as IG and 50G, or we can use the instantaneous overcurrent of unused 3-phase bank and CT instantaneous overcurrent elements as the check zone. And then the logic would look as follows. So first of all, the differential function, for example, the A phase, will be supervised with the instantaneous overcurrent of the A phase. And the instantaneous overcurrent responds to the externally formed differential current. And then, of course, each of these 3 can be ORed and be used as our differential trip function command. Let's have a look at 4 examples of how our external check zone can be used in the B90. So in this case, version 1, we have 2 CTs wired, one CT to relay A and one relay to relay B, but both measuring A phase current. So in this case, relay A would calculate differential and determine if we should trip, and relay B would be the check zone doing the same zone, and if it determines it must trip, it would send a permission signal or a supervising signal to the relay A. Now, you'll notice that there's also the critical fail from relay A that allows tripping to go through for in case relay B failed or is out of service. So this allows for a very strong security based on a 2 out of 2 independent relay scheme. Version 2, we have 2 current transformers and each of them wired to 2 separate inputs and the same relay doing the same differential calculation. And the supervision or check zone supervise the A phase and determine if the relay should trip. So we again have a 2 out of 2 scheme here. However, everything is in the same box, meaning wiring is simpler. Now version 3 is very similar to version 1. The only difference is in this case, both relays A and B are wired to the same current transformer and wiring. So in this case, relay A and the check zone in relay B would get the current, calculate the differential, and relay B again will send the permission or supervision to relay A to determine if it will trip. Now the 4th version is again having only one current transformer but wired to the same relay. So in this case again one relay is doing the differential and has the check zone. So this is easy to wire since there's no inter-chassis wiring, and it safeguards against relay problems and bus replica problems. Another method of doing supervision is to use undervoltage. Now, during any power system fault, we always have a drop in the voltage. And this is the principle we can use here. So we can use undervoltage to supervise the differential function. Now, for speed and sensitivity, the undervoltage should be set pretty high in the range of 0.85 to 0.9 per unit. And to make it more secure, we can use 3 undervoltage elements per bus per phase. For example, for the A phase differential, we can supervise it with undervoltage functions A to ground, AB, and CA. And in that case, we can alarm on spurious differential currents. And this would safeguard against CT problems and AC wiring associated with CT and CT wiring, problems with auxiliary switches for breakers and disconnects, including the isolators and isolator monitoring, DC wiring problems associated with the dynamic bus replica, and failures of current inputs to the relay itself. Let's have a look at two examples of how undervoltage supervision can be used in the B90. So in this case, the B relay will monitor the A voltages and determine the logic and send the permission through to the A relay. The A relay will measure the currents, calculate the differential, and based on the supervision from the B relay that determine the voltage, will give us a permission to trip. Now, to safeguard against if the B relay failed or is out of service, we still would have the critical fail wired to the A relay, equivalent to that we've seen in the check zone examples. Another example is to do everything in the same relay or box. So in this case, the A relay will monitor the A phase voltages and also the A phase currents and calculate the differential, and this will be supervised with the voltage function. Now this is simpler to implement since there's no inter-chassis wiring. This concludes our webinar for today. So in our webinar, we discussed the configuration of the bus differential, the settings, adaptive logic, how to do it and what it means. We discussed some application considerations for the B30, B90 and the B95 Plus. We went through some advanced application topics, and in our next and final webinar, we'll cover the B90 and B95 Plus examples. For more information, please visit our website at www.gedigitalenergy.com. Thanks for watching.